let's look at page 257, example 3.28, which is a short little example but demonstrates an interesting point of how to use different rules together. So example 3.28, we have a function that's called k of x. K of x is 3 times h of x plus x squared g of x. Now we don't know what h and g are, but it doesn't matter. We just calculate the derivative as much as we can. So the goal is to find derivative of k. To find k, we will use, see, there's a product here, so we will use the product rule. And there's a sum here, so we'll use the sum rule. And here's a multiplying by a constant, so we'll use the rule of multiplying by a constant. And here's x to the power squared, 2, so we will use the power rule. So we'll use all those rules, and to get it done. So to do that, we write down k prime of x, and so the constant multiple rule or something like that says you just write it down, 3h prime of x. So far so good. And being that we don't know what h is, this is all the derivative we're going to go. Next, plus, now we have to do the product rule for this thing. So the product rule is right here, is if you have f and g, two functions that you have to take the derivative of, the product rule states is the first term times derivative of the second plus the second term times derivative of the first. So that is roughly the product rule. So we'll follow this product rule and says we'll take the first one, x squared, times, we'll put some parentheses here so that we know that we're applying the product rule to this particular thing. So we take the first term times derivative of the second, which is just g prime of x, plus the second term. What's the second term? That's g of x times derivative of the first, which is 2x. G times 2x. Okay? Because the power rule says you take the coefficient on top and slap it to the front, and then x has a power 1 less. That is, the power rule says that the derivative of something with a power is nx to the power n minus 1. See, so that's what I'm using here. And so after that, that's about done. Okay, you might clean this up a little bit as your book has it. But generally speaking, that's about it. Now notice that your book used the d by dx notation, which is perfectly fine, right? But I feel like this way, if you use the prime, you do a little bit less writing, like all the d's. You can skip some of the d's. So for this particular example, I prefer to do it this way. But you can do it either way, it's fine. There are situations where the d by dx notation might work out better. It really depends on, it's really a matter of preference. So we're done with example 3.28. Let's move on to example 3.29. Next, same page. Example 3.29 says that you have a function, okay, which is called k of x, which equals to f times g times h. And you don't know what f, g, and h are, but you're supposed to find the derivative of k in terms of the derivative of all this stuff plus the function themselves, just, work it out the best you can. Let's say so what is the derivative of k? Now to do that, we have to apply the product rule, but the product rule only talk about 2 items. Now we got 3. Now what are we gonna do about it? The way to do it is we'll call 2 of them as a group. So we'll pretend that there's only 2 things by calling these 2 one thing. Okay, so we will put parentheses here or brackets, either way. So now we have 2 things. Okay, we'll have this thing and that thing. the first we'll do the derivative of this. Well, let's call this one, your book doesn't do this, but I feel that this is a little bit cleaner in the sense of organized. Okay, let's organize. Let's call this thing j of x. Such that, so we have right now j equals to f times g. Okay, I'll skip all the x's for now. So then j prime, which is the derivative of j, equals to, according to the product rule, f times g prime, okay, plus f prime times g. Okay, that's the product rule. Each one gets to do the prime ones and keep being the original ones. That's how it works. So then substituting this thing back in here, we get k equals to, we'll skip the x's for now because the x's don't do much in this problem because, yeah. Anyway, so k would be equal, so when, right, let's see. So k prime, okay, equals to first term j times the derivative of the second, which is h prime, plus the second term h times derivative of the first, j prime. Right? So far so good. I'm applying the product rule, this one, and which equals to, then we'll write it out. What is j itself? J is just f and g, which is fine, times h prime plus h times j prime. J prime is this stuff, so f, we worked out j prime right here. So I'll copy it down, f prime g. All right, so then let's write this stuff all out. That equals to f g h prime, okay, that's the first term, plus f g prime h, f g prime h, okay, that's the second term. I rearranged it alphabetical order. And thirdly, the third one's h, f prime h, f g h prime, okay, f prime and g and h, right? So you notice this is the answer. That's the same answer your book has, except that there are a lot more x's in there, but we don't need to write the x's because the x's don't do anything in this particular problem because they're just generic functions. We don't know what they are. So, but you notice a pattern, especially without the x's. So you have three things multiplied together 3 times. All 3 items in here. We started out at FGH. So you have FGH multiplied together by itself 3 times, except that each one get a derivative one, on here. See, FGH prime, FG prime H, and then F prime GH. So all 3 things, and this is all symmetrical and evenly balanced. Each item that we were multiplying with gets to do the prime 1 time, and then no prime 2 times. And that is how the derivative of 3 items happen to work out. Alright, so that is nice and clean, right? So next, we will find, let's example 3.30, which I will assign as homework. What happens is you have to, now you have a fraction and a bunch of stuff. So what do? Well, you apply the rules one at a time. I recommend that you, at the bottom, the denominator looks fairly clean, 3x plus 2. The numerator is a product, right? You have 2 items. You don't know what k is. Doesn't matter. You just work with it like you do here. Your result will be in terms of derivative of k or k itself, or both. So what you're going to do is, I recommend, the book doesn't do it, I recommend that you let the numerator be a j, kind of like what I did here, to make it a little bit more organized. But you don't have to. You can just do it like the way the book does it. But please do perform example 3.30. It's a bit tedious, right? It goes on. Your answer is this huge thing. So, but do not be frightened by how long it is. Okay, it's a long answer is no harder than a short answer. They're the same thing. And you got the answer, you understand it. See, so as long as you understand it, math is never hard. So let's move on. So example 3.30, which I will write down as homework. Now the same can be said of the next example on page 259, example 3.31, where you have to find the horizontal tangent. The problem is fairly straightforward. You figure out where the derivative is 0 and solve for x. And next example, and that will be in your homework. And the same as example 3.32, the next one on the same page. When you find some velocity of something, you find velocity. What is velocity? Velocity is the derivative. So you take the derivative, and then you need to figure out when is something like 0. What is the velocity when at time 0 or 1 or whatever it is? Then you just substitute, put the time in, and calculate it. So, and I think those are fairly straightforward, so I will have you do them as homework. Now with that, we come to the end of the section. This section is a little bit long, but don't let that discourage you. In the past, a couple of chapters, we have been going through it because they're just building the calculus. But now we are in calculus. This is calculus. Okay, we're in differentiation, so we need to put in a little more time and deal with a little more symbols. Some of the answers might be, your page might not be long enough, wide enough to write the whole answer in, and that's the way it is. Okay, you're in calculus, right? I mean, it's not some cute little answer like you did in algebra anymore. So let's do that. And so next, let's get to the homework. I will post the homework below this video, but I'll also read it out loud. Which homework is on page 263, and please do problems 108, 111, 113, 116, 120, 125, 128, 130 part B only, 134, 140, 142 part A only, and 144. And that's the ones I chose. So please go do your homework, and when you're done, I am going to next look at a couple of homework problems. Now I know that for this section, the section seems a lot longer with a lot more stuff. It's just maybe it would have been better if the book has made it a shorter section in like 2 sections instead. But being that that's how they design it, that's how we're gonna do it. So please do all the homework patiently. It takes effort it takes patience to get through it all, but it's very good for learning calculus. And so for the homework problems, I find them mostly fairly straightforward. The most interesting one is problem number 140, and that's the one I will go over right now. So problem 140, and that's on page, I guess 163, 263, I mean. All right, let's look at problem number 140, which says something like, you have an f of x, which is equal to x to the power 3. Okay, that is a standard math problem. I mean, that's a standard graph. And you should be able to remember what that thing looks like. If you don't remember what x to the power 3 look like, you should plot it right away on the graphics on the decimal graphics calculator, or whatever that thing is called, graphing thing. The x to the power 3 looks something like this. It goes, okay, it's just something that you should be able to visualize in your head and have it memorized. So then what does this thing want? It wants to know at which point the tangent of this thing is going to have an x-intercept of x. So at a certain point, let's call it A. At some point on here, A, if x is A, then the other point will be A to the power 3. Okay, at some point on here, A and A to the power 3, the tangent happens to have an x-intercept of 6. So we need an x-intercept equal to 6. All right, so how do you do that? The way you do it then is make out the equation for this thing. Now the equation, first we'll figure out what the tangent is. The tangent is the derivative. So we have f prime. First we calculate f prime of x, which is equal to, by the power rule, 3x squared. Okay, you take that one, put it in front, and then reduce it by one number. So 3 becomes 2, and the 3 goes in front. So that is the derivative. Once we know that, then therefore f prime of a, which is the slope of this tangent line that we're interested in, is f prime of a equals to 3a squared. And we still don't know what a is, but the a is what we're looking for. But we have a condition that will help us track down a. What is a? So the condition is that the x-intercept of some point a, let's say is here. It might, here's our point a3. I don't know that it's there. It's just a visual tool. It might be over here. But anyway, there's some tangent line, okay, where it has to intercept x at 6, which this is not gonna, because this is on the negative side. Maybe I should have drawn it over there. Yeah, let's draw it over here. Here's our new a cubed. And such that when you go down, the x-intercept is at 6. Okay, and yeah, I'll leave that one there, because that's just a guess. Okay, we don't know exactly what a is, but it's probably over here, so that we can hit the x-axis at the positive value of 6. Having seen that, now let's figure out what the equation of the tangent line. The equation of the tangent line, as always, we're going to use the point slope formula, which says this: m equals to, m is the slope, y minus y1 over x minus x1. That is the point slope formula, which you totally need to memorize. Which in this case, where our x1 and y1 equals to a and a cubed, because that's our point. This is our point, so that's what it is in the formula. Now, and remember all these x's and y's and 1's, they all mean something. See, the x1 and y1 is a particular point, whereas xy here is the variable in your formula, and m is that slope. So in our particular situation, our point x1, y1 happens to be a and a to the power 3. Now, knowing that, then let's write down our tangent. So our tangent formula is y minus y1, which is a to the power 3, divided by x minus x1, which is just a, and that equals to m, and the slope of that point is the derivative, which is 3a squared. All right, now, and okay, now we got a lot of variables, but actually we need the x-intercept to be at 6. What does that mean? That means this particular line, tangent line, goes through a point where where x is 6 and y is 0. So then, so we can plug these numbers in. So this line, when y is 0, x will be 6. We'll put that in. So 0 minus a cubed over 6 minus a equals to 3a squared. All right, now you have an equation with only one variable, which is a, and a is what we've been looking for this whole time. So now we are going to be stuck in algebra. Okay, let's solve that equation in algebra, and there's no getting around it except to work on this thing. So we'll write down the equal sign. Multiply the bottom over here. 3 times 6 is 18. A squared minus, that's 3a cubed. And then the last one is, that one becomes a plus a cubed. Okay, I move this to the other side, and this becomes a 0. And then, all right, so that becomes give me a second. well, I did it slightly differently earlier, but it doesn't matter. The point is we have then we have 3, that's minus 2 over here becomes plus 2a cubed equals to 18a squared. Let's cancel out some a's, then that 2a will be 18, and then a equals to 9. And then a to the power 3 is 9 to the power 3. So the answer is, which we're looking for, at which point that this tangent will intercept at 6? Well, the answer will be the point 9 comma 9 to the power 3. Did it? And what is the tangent itself? The tangent itself, then when you plug the value of a into here, then you get something like, eventually, after all the dust cleared, well, actually, we'll just plug it in. The tangent line is y minus 9 to the power 3 equals to the slope, which is 3 times 81. Okay, 3 times 81. It says here, slope is 3 times a squared, 3 times 81, and then x minus 9. And if you clean that up even more, then you get something like this. Y equal to 243x minus 1458. Now the graph of this thing, if you were to graph it on the decimal calculator, then you will see something like this, except it's a lot more slanted. The graph I drew, it ended up looking like this. And the x, this thing is hitting it way up there, okay? Because it intercepts at 9 cubed. 9 cubed is 729. So it's going to hit it way up there. But that's the answer to this problem. And that marks the end of this section.